Hello everyone, welcome to my physics class, Standard 8, Chapter 4, which deals with energy. In this chapter, we will study about work, energy, energy transformation, and power. We will discuss about all these topics one by one. Let us begin the topic by discussing about work. So, in our day to day life, we use the word work, we play, we sing song, we write, we read, we walk on the road, we cook. In our daily activities, we do all these works. Thus, in our day to day life, we consider any useful physical or mental labor as work. But in general words, in general language, this is the that we mean about work. But in physics, the term work is defined differently. In physics, work is said to be done only when a force applied on a body and displaces a body to a certain distance. Then work is said to be done. Some examples of work done are: a man pushes a car and moves it. The man pushes the car, and when it pushes the car displaces along the direction of applied force. So we say that work is done in pushing the car. A boy pushes a heavy box to change its position in the room. When a boy pushes a heavy box, the position of the box changes. So we say that work is done in changing the position of the box in the room. A player kicks a football towards another teammate. While playing football, a player kicks a football towards another teammate. At that time, the force applied by a player and the ball displaces to another player in the direction of applied force. So we say that work is done here in this case. So in the examples given above, objects, that is the heavy box and the football, changes their position when force applied on them. So we say that work is done by them. On the other hand, when we try, look at this figure, but in other hand, when we try to push a wall but it doesn't move even a bit, thus no work is done in this case. If we want to push a big wall, the wall doesn't move at all. We apply force on the wall, but the force does not displaces the wall along the direction of applied force. So no work is done in this case. Suppose a body is kept on a smooth horizontal surface. This is a smooth and horizontal surface, and a force F is applied on the body. You see here, force F is applied on the body, and this force acts on the body for some times, during which the body changes its position. It was the initial position of the body, and when the force applied, the body moves along this direction and reaches to another end of the table, and that is the final position of the object. This is and the end of the table on which the table is kept initially, and where we apply force, is the initial position of the object, and after applying force, the object displaces. This arrow mark shows the direction of displacement, displaces along the direction of applied force, and reaches another end of the table. So it is this change in overall position of an object is called the displacement. The displacement is denoted by symbol S. Displacement is denoted by S. In such cases, so work done is equal to force into displacement. Work done is equal to force and displacement. Thus, work done by a force on a body is the product of force into displacement. You see, work is equal to force into displacement. So work done can also be defined as the product of force and the displacement of the body. So W is equal to F into S. W stands for work, F stands for force, and S stands for displacement. So the unit of work is joule. If the displacement of body is 1 meter by a force of 1 Newton acting on it, and the direction of displacement and the direction of displacement, then the work is said to be done 1 joule. Let us again define the work done 1 joule. The work is said to be 1 joule when a force of 1 Newton is applied on the body and body displaces through 1 meter along the direction of applied force. Now some numerical problems. A force of 10 Newton is a force of 10 Newton acts on the object. The displacement is 8 meter and the direction of force. Find the work done. Here given that in the question, the question conveys the information that force is equal to 10 Newton, displacement S is equal to 8 meter. It is asked in the question to find the work done. So we know that W is equal to force into displacement, work is equal to force into displacement. Here force is the 10 Newton and displacement is the 8 meter. So 10 into 8, 80. You know that the unit of force is Newton and the unit of displacement is meter. So unit of work is Newton meter. So work is equal to 80 Newton meter and 1 Newton meter is equal to 1 joule. Therefore, work done is 80 joule. "40 joule of work is done when a force of 20 Newton is applied on a body and causes a displacement and the direction of applied force. Calculate the displacement." You see here, the question gives the information that work done W is equal to 40 joule, force is equal to 20 Newton. And now we use the relation that W is equal to F into S. We have to find here the displacement. In the question it is asked to find out the displacement. So S is equal to W by F. Now substitute the corresponding values of W and F. W is equal to means work is equal to 40 joule by force is equal to 20 Newton. So 40 joule by 20 Newton. So 40 by 20 gives 20 and unit of displacement is meter. So S is equal to 20. Sorry, S is equal to 2 meter. S is equal to 2 meter. Displacement is equal to 2 meter. A pair of pulley exert a force of 1400 Newton on a plug. The field being plugged is 15 meter long. How much work is done in plugging the length of the rod? You see here, force applied is 1400 Newton and displacement, since the length of the field is 15 meter, so displacement will occur along its length. So S displacement S is equal to 15 meter. So work done W is equal to F into S. So 1400 into 15, that is 21,000 joule. So work done is equal to 20,000 joule. Example 4. Calculate the force applied on a body when it is displaced by 5 meter and 500 joule of work is done. In the question it is given that W is equal to 500 joule, displacement S is equal to 5 meter, and W is equal to force into displacement. So, or F is equal to W by S. So work done is equal to 500 joule and displacement 5 meter. So 500 by 5, that is 100, and unit of force is Newton. So force applied F is equal to 100 Newton. Now I am going to discuss about energy. Energy, the ability of doing work, is called energy, or the capacity of doing work is also known as energy. Energy appears in many forms. It means that energy exists in different forms in the nature, and one form of the energy is mechanical energy. Mechanical energy is the energy possessed by a body by virtue of its state of position or motion. In other words, we can say that total mechanical energy of a body is the sum of its potential energy and kinetic energy. Mechanical energy is of two types. One is potential energy and kinetic energy. There are two types of potential energy. So the total mechanical energy of a body or the total mechanical energy of a system is the sum of its potential energy and kinetic energy. Now first we discuss about potential energy. What is potential energy? The energy possessed by a body due to its position relative to another object is called potential energy. An object may store energy by virtue of its position. In this state, the object has the potential energy for doing work. When the body is kept at a certain height, at that time, the body has the capability of doing work since it possesses the potential energy. Water stored at a height possesses potential energy due to its position. The height of the water provides the necessary potential energy, and when the water falls from a certain height, it rotates the blades of the turbine, which in turn generates electric energy. A body dropped from a height, for example, a fruit is falling from a tree. A body dropped from a height falls to the ground. This happens due to the work done by the gravitational force acting on the body. So what is gravitational force? The gravitational force of attraction acts on the body in the downward direction. Gravitational force always acts every object in the downward direction towards the surface of the earth. So clearly work is done by the gravitational force. If you throw a stone upward, after some time the stone falls on the ground. The gravitational force attracts to pull it down again. On the other hand, if we want to lift a box, we appear. If we want to lift a box, we apply force on the body or on the box in the upward direction and displaces it through a certain height. Obviously, we do some work on the body against the gravitational pull. By displacing a body at a certain height from the ground, we do work on it, and this work is possessed by the body as the energy which is known as the gravitational potential energy. When we do work in hand, and this work is possessed by the body as the energy which is known as the gravitational potential energy. So now let us define gravitational potential energy. We define gravitational potential energy as the energy possessed by a body by virtue of its position with respect to the surface of earth. It means that when a body is kept at a certain height, the body possesses gravitational potential energy. So, gravitational potential energy is calculated as gravitational potential energy is denoted by capital U, and gravitational potential energy is equal to mgh. Where m is the mass, g is the gravitation acceleration due to gravity, and h is the height of the object. Once again, U is equal to gravitational potential energy U is equal to mgh, where m is the mass of the object, g is the acceleration due to gravity, and h is the height of the object. If mass has the unit of kilogram, acceleration due to gravity has the units of meter per second square, and height has the unit of meters, then the gravitational potential energy has the unit of kilogram meter square per second square. So U is equal to mgh. Now substitute the corresponding unit of mass mg and h. So kilogram into meter per second square into meter. So that gives U is equal to kilogram meter square per second square. It is the unit of the potential energy, gravitational potential energy. From the expression U is equal to mgh, we can conclude that the gravitational potential energy of an object depends upon the weight of the object, that is mass of the object, and acceleration due to gravity. You know that weight is a force. So force is equal to mass into acceleration. Here m stands for mass, and g is the acceleration due to gravity. So that m into g gives the weight of the object. The vertical height of the object from the earth's surface, the vertical height of the object from the ground means the height at which the object is placed from the ground. So generally, energy is measured in joules. So 1 joule is equal to 1 kilogram meter square per second square. So it means that 1 joule is equal to 1 kilogram meter square per second square. This is all about the potential energy. Now we discuss about kinetic energy. Kinetic energy is the energy possessed by a body by virtue of its motion. It is called kinetic energy. To set a body at rest into motion, we apply force on it. When we apply force on the body, it sets the body in motion. The body gets displaced and thus work is done. So this work done on the body is stored in it in the form of kinetic energy. The work done on the body is stored in it in the form of kinetic energy. So the body which is set in motion can also put another body which is at rest into motion. For example, a moving billiard ball hits another stationary ball and sets it in the motion in the game of carom board. If we strike the coins of the carom board with the striker, the kinetic energy of the striker sets into motion into the another coin, and the coin which is in motion, if it hits to another coin, that coin also sets into motion. So the kinetic energy, so when the body is in motion, it possesses kinetic energy. Examples of kinetic energy: wind possesses kinetic energy, and this energy is used to rotate the blades of a windmill. A bullet moving with high velocity. You see, a bullet moving with high velocity possesses kinetic energy. Due to this, the bullet can penetrate the object it strikes. A fast moving stone possesses kinetic energy. Due to this, it breaks a window pane on striking it. You see, if we throw a stone towards the window pane, it strikes the window pane and breaks it. So these are the examples of kinetic energy. To calculate the amount of kinetic energy, we must know the mass and velocity of the body. The kinetic energy, the velocity of a body, is the rate of change in the position of the body. And velocity has magnitude and direction. So it is calculated as velocity v is equal to change in displacement by change in time. So kinetic energy is calculated as kinetic energy is equal to half mv square, where m is the mass of the object and m is the velocity of the body. If mass has the unit kilogram and the unit of velocity is meter per second, then the kinetic energy has the unit of kilogram meter square per second square. You see, kinetic energy K is equal to half into m into v square, half into mass of unit of mass is kilogram into unit of velocity is meter per second square. So kilogram meter square for second square. So 1 joule is equal to 1 kilogram meter square second square. We know that we generally express energy in joule. So joule is the unit of energy. So this is all about work and energy. And then next video lecture we discuss about the transformation of energy and power. Thank you.